as I said on Tuesday, I guess it was, or Wednesday, all the days seem the same. We'll continue a tiny bit with the lecture and then move into the practice class. So just a summary of where we were at the end of the last lecture. So we're talking about matrix representations of linear transformations. And remember, the point of that is that once we've got, let's say we've got finite dimensional vector spaces, once we fix a basis, then then that vector space is going to be isomorphic to Fn for where n's the dimension, with that isomorphism depending on the basis. And once we've made those choices, then any linear transformation from, let's say, V to W, with a basis in V and a basis in W, can now be represented as a matrix. And that's what we went through last time. And so let's go through that again. So we've got a linear transformation theta from V to W. We've chosen a basis of V. That's going to be called B1 up to Bn. So V is n-dimensional. And then A1 up to Am, an ordered basis for W. Once we do that, the matrix of theta with respect to these bases is the matrix. It's got m rows and n columns, and its jth column is given by, so you have to make a computation to find the jth column. You compute this theta of b subscript j, write it out in terms of the basis of W, so this is an element of W here, write it out in terms of the basis of W, and those coefficients that you get in that linear combination form the jth column. Okay? So today we'll do a few examples. And just to put that another way, I don't know if it's any more helpful, but this is like a more formal definition, let's say. That's the matrix of theta with respect to these two bases is C subscript ij, the matrix whose entries are Cij, and the Cij's are given by this formula here. But that's exactly what I was saying. That's the jth column now is, when you read this formula, the jth column of the matrix is the coefficients when you expand this in terms of these basis elements. That's exactly what we're saying. That's frozen on the other screen. But maybe what I didn't say right at the end of yesterday, or last time, was the following. So the point of this, or the way it's working now, is if you have a vector V in your domain, so V is in V, that means it can be written as a linear combination of the B's, the basis of V. Then what this matrix is doing is the following. It's computing the coefficients mu, 1 up to mu m, where theta of V is written in the basis of W, and it's doing it exactly by matrix multiplication. So in the land of linear transformations, the connection is this. V goes to this, theta of V. But in matrix world, it's just matrix multiplication. So you take this matrix of theta that we've just defined, multiply it by, so basically what you're doing is you're just imagining this guy here as you're forcing it to live in Fn via the isomorphism after choosing the basis by just taking that thing and identifying it with this thing in Fn, and then matrix multiplication tells you what the mu's are, is the point. Okay. So that's the point. So it's clearly something you want to do. For example, if you had an abstract-looking linear transformation, pick your favourite bases. There might be a reason why you choose one basis over another, but anyway, there might be some favourite basis you pick. Work out the matrix, and then that's something that a computer would lap up or whatever. You don't have to program some kind of exotic vector space and exotic linear transformation. You just have to tell the computer to do matrix multiplication, which it already knows and does ultra efficiently. All right. So everyone clear what the point is? Because sometimes people just don't know what the point of matrix transformations are, of matrix representations. That's the point. So to find examples, it's really, really easy. You just need to practice. You just need to remember what the process is. So here's so this first example is one where our linear transformation is going to be given already by a matrix, but for reasons unknown, I mean for reasons that are sort of hidden in the example, we may want to work with some different basis of the the domain and codomain. So here's a different basis of the domain of f of this one, and here's another basis of the codomain, and so this linear transformation will be now written in terms of, as a different matrix of course, but in terms of this basis, these two bases. So how we do it is exactly the, oops, sorry, something's going wrong with my freezing there. We do it exactly the way our recipe said, so we take the jth, well, we have to do it for all of them, so let's start with B1, then B2, then B3. We compute theta of B1, theta of B2, theta of B3, and then we do the working involved to write theta of B1 as a linear combination of A1, A2, A3, A4, theta of B2 as a linear combination, and so on and so forth. And that'll tell us first column, second column, third column, third column. Yeah, there'll only be 3. So how does that go? Oh, sorry, I already froze that one. Let's write what we have to do first. So we want to find, so we'll try to see how to do it relatively efficiently as well. So we want to take theta of B1 and write it out as a linear combination of the A basis. It's always a bit of a pain which way the C, it's not C1, 2 there, it's C2, 1, because that first calculation tells me a column of my matrix. So that's why it looks a little bit transposed somehow. That would, the coefficients here give first column of our matrix representation. And I want to do the same thing. You wouldn't necessarily write this out each time in your solution, but I'm just going through it a bit slowly the first time. Oops, not A though, C. C3 to A3 plus C4 to A4 theta B3 equals C1, 3 and so on. 3, 3, 4, 3. So to do this fairly efficiently, we work as follows. So first, we need to compute all theta B subscript j for j equals 1, 2, 3. And we can do that all in one go. We've got our matrix over there, which are called M. So I want to do M applied to, what do I want to do? Well, to find for B1, I have to put the B1 there, but then for B2, I have to put a B2 there, and then a B3. So I could just put that matrix with first column B1, second column B2, third column B3, and just do that matrix multiplication, and then that'll tell me each of those things. So I just put a B here, because it is the B now. I'm using B without the curly thing under it to mean the matrix whose columns are the basis vectors of B with the funny squiggle underneath it. In other words, this is, so M was over there, but I've got it written here, a bit easier. 1, 2, 0, 2, 1, 1, 0, 1, 1, 1, 1, 0, I think. B, if I put all those basis vectors into a column, it's this, this, and this. And the point is, the way matrix multiplication works, matrix applied to vector 1, vector 2, vector 3 is just matrix of vector 1, that's the first column, matrix of vector 2, that's the second column, matrix times vector 3 would be the third column. So it's sort of making matrix multiplication work block by block, which I guess you're somewhat familiar with. And we compute this. We're working over F3 here. And I'll just copy what I did earlier, assuming it was correct. So I'm just doing matrix multiplication there. So what I'm finding there, this column is theta of B1. This one is theta of B2. And this one, theta of B3. Okay, so it's a bit more efficient than doing them all at once somehow. Well, it's exactly the same, but it just feels a bit more efficient. Next step. Now need to find, to solve the systems, which I'll call dagger, which I didn't give a name to earlier. That's these. So what do these look like now? I've just computed all of the, where's it gone? Up here. I've just computed these three vectors, so now I have to find these linear combinations. So that's another matrix calculation. So that really there's three systems to solve. But we can do it all at once. So the way we do that, take the matrix A, which is A1, A2, oops, no comma, A3, A4, augmented with theta of capital B, which was the matrix theta B1, theta B2, theta B3. And now do the row reduction. What have I said here? Yeah, okay, good. Just a comment, before we even make the calculations, let's see what we expect here. So since the columns of A form a basis, we know that A, when we do the row reduction, will reduce all the way down to the identity. So that's something you would have discussed last year and we'll touch on a few more times in this course. And so what we already know what we're kind of expecting to see here. We're expecting to see, after our row reduction, reducing down to the identity, and then something here. And then by solving the equations, well, this is now, so we don't have to even do back substitution. This is just identity equals this. So our coefficients are exactly this matrix C. So ourCij's that we're trying to find are precisely the entries of this matrix C. Okay. So let's do the details. But maybe I'll be a little bit quick with the details. So theta, A, augmented with theta B. Yeah, let me just say row reduces all the way down to identity matrix And what I get on the other side was 1, 2, 0, 0, 1, 2, 2, 2, 2, 0, 0, 0. So theta, the matrix of theta with respect to base is AB, is that matrix we just worked out. Okay. Any questions about that? So you might have to maybe go through a bit more slowly what we're doing, how doing this row reduction is equivalent to solving these equations. But that sort of clear. I mean, just let me try to emphasize that again. I mean, this first equation here actually is itself, just to unpack things a little bit, this first equation is already itself a system of equations because it's a vector equation. So this guy here is a length 4, a vector, with 4 components. Each of these have 4 components. So that's actually a system of 4 equations in the unknowns. So that's what we're solving that. And then we're solving this system of 4 equations in 4 unknowns, the unknowns being the C's. And then we're doing this one, and so on. Okay. And we're doing it all at once. So we're solving 4 systems of 4 equations, all pretty relatively quickly. So that's why it was worth trying to do it efficiently rather than do it one by one. Yeah?
So you know the matrices are
Say again?
they're not like high-five.
Yeah, except this we haven't got square matrices. Oh, sorry, yeah, this A, yeah, definitely. So this A here, we'll come back to that in a few minutes. Yeah, this A, so this process here of row reducing A, so A was these 4 vectors formed a basis, and the process here, so you can indeed, yeah, good. Let's say that now. Yeah, good. Note, the way to find an inverse of A, we do the row reduction A, and we stick the identity on there, and row reduce away to get the identity, and whatever we get on the other side is the inverse of A. So you remember that process? Finding an inverse for a matrix. And to think of what you're actually doing there, we're going to talk more about row operations, even though you already know them, but a bit more formally next week. But what this process does is each time you're doing a row operation, you're left multiplying this by the elementary matrix corresponding to that row operation. Okay, so really there's sort of an equation going on here saying that when you take A, well, AI, let's keep it like that matrix, and we start multiplying by all of the elementary row operations we do to reduce A, the left-hand side, and we do that, left multiply them there, we get A inverse. But so what that's telling us actually is that what do I want to say? Yeah, so the product of these I's now, it's the product of these E's, is the inverse. Because it's a thing that when I multiply this onto A, I get the identity, so that's the inverse. Okay? Or maybe think of it more clearly, multiply it into this component and it becomes the inverse. And the process of doing the row reduction is just multiplying by the inverse. So in summary, that means that so in the working above, what we did was row reduce A with this matrix theta B down to the identity. And we got C. But the thing that does that, the thing that performs those row operations, is multiplying by this inverse, this product of these elementary row operations. So, in other words, it's actually an equation here. A inverse times this augmented matrix equals IC. Therefore, let's say, A inverse theta of B equals C. So we do have another method that we could have done to solve this system of equations, is to instead multiply by the inverse. Okay. Theta of, the matrix of theta with respect to AB is A inverse times theta of B. In this case. Well, I mean, I say in this case because our A's and B's were already vectors in Fn. I mean, because we had this sort of this situation where we were, yeah. Good. However, notice it's the same amount of working. To find the inverse, you have to do the, so compare the two processes. To find the inverse, you have to do all the row reductions to the left-hand side and follow it on to the right-hand side to work out what the inverse is. And then you'll have to do this matrix multiplication. The way we did it initially, you just do the row operations that you need to do, find the inverse, and as you go, you just do them on the other side. So, I mean, it's equally, I guess it's equal, arguably a bit quicker because we don't have to do the extra matrix multiplication later. But they're basically the same, yep. Good, I think and I'm going to make a further comment about that, and I think it's next week. Oh no, here we go. Sorry, I do have a comment coming up. I was about to say exactly what you just said. But anyway, we just said it. So, okay. Oh, here it is. Okay, I think this is what I just explained. Sorry, I should have read this before. So, recalling that A inverse is computed by doing this row operation, we have another formula. There we are. Sorry. That would have been quicker. Good. Yeah, I said the same thing twice. One more example, maybe. There's another example coming up, but maybe I'll leave that one as an exercise. So here's one where let's mix things up a little bit more and work in a not an Fn vector space, like just some more exotic looking thing. So we look at this 5-dimensional vector space over Q of polynomials of degree less than or equal to 4, going to 4-dimensional vector space of polynomials of degree less than or equal to 3. And the formula is just using this formal derivative, which is just the derivative now because we're working over the rational numbers, but anyway. There's lots of different choices of the bases we might want to choose. A natural choice of basis would be this for the domain and this for the codomain. To find the matrix of differentiation with respect to these, we have to compute all of these things. I mean, this example will be a bit quicker. We compute d, the derivative. That's our name of our linear transformation. D of 1, well, I have to compute that. It's, of course, just 0, but I have to write it back in terms of the basis. So that's 0 times the first basis vector of this. I'm writing it in this the basis vector of this guy. Plus 0 times x, plus 0 times x squared, plus 0 times x cubed. Anyway, so that first column, so I don't have to do any solving systems this time. The last example required a bit of work. This one, it's immediate. The first column is just going to be 0, 0, 0, 0, however many zeros? 4 zeros. D of 1, that's, d of x, sorry, that's 1, which is 1 times 1, plus 0 times x plus 0 times x squared plus 0 times x cubed. D of x squared is 0 times 1 plus 2 times x plus 0x squared, and so on. And d of, I have to go up to x4, so I've got to do x3 and x4, 0, 0, 3, 0, and finally 0, 0, 0, and 4. So we're done. There's no further calculations in this one. Hence, the matrix, oops, not theta, matrix of D with respect to these bases is just 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Oops, I needed some. A 1 there, a 2 there, a 3 there, and I need one more column with a 4 there. Okay. Right, so that's much easier. So notice when there's work involved, normally when there's sort of work that might be involved is when you compute these values and it's hard to write them in the basis of the codomain. That's when you have to do the calculation we were doing earlier. Sometimes it'll just be obvious, like how to write them in the basis of the codomain. So I've got some other ones here, but I'll leave these as exercises and we'll move on to the practice class. So here's another one working over Z3, polynomials with coefficients in Z3 with some double differentiations and stuff. We can work with the same basis on both the domain and the codomain here. And in the last example, which is even more exotic in a way, here we've got our polynomial of degree less than or equal to 2 with rational coefficients, and we go about evaluating it at square root of 2. So that takes us into this vector space. First, you should check this really is a linear transformation. Exercise, it is. And you can compute the matrix of it with respect to all kinds of different bases, but here's a pretty random choice of basis vectors for the domain and some also fairly random choice of basis vectors for the codomain. And as an extra exercise, you could check that they're the basis vectors. And I'll just write the solution for that one for you to check. So you should get theta AB equals 1, 8/5, 3, 0, 4/5, 1. Good. Okay, so any questions about matrix transformation? Matrix representations? All right. So, moving on today to the practice class, worksheet 3, I think, or 2? 3? Here we are. So the worksheet for today doesn't have things about matrix representations, but we just did some examples of those anyway. The topics in the worksheet today are about just linear transformations themselves, and then image and kernel, finding bases of images and kernels. So this first one, we're asked to do all kinds of things. We've got a function between two vector spaces, and we're asked to decide whether it respects the scalar multiplication, respects the vector addition. If it does both of those, then it's a linear transformation. And then if it's a linear transformation, then answer the questions of whether it's injective, surjective, and if it's both, then it's bijective. So the first one there, the identity map. Is that a linear transformation? Yeah. If that's not a linear transformation, I don't know what is. That certainly is a linear transformation. Is it injective? Yeah, it sort of better be everything, really. So it's indeed bijective. Okay, that one's an easy one. Now the zero map. So this takes everything in the vector space V and spits out the zero vector. Does that sound like a linear transformation? Certainly does, yeah. Is it injective? Certainly not. It's mapping lots of things to zero. I mean, if the dimension of V was 0, then, okay, it would happen to be injective. So that's eliminated by that. Surjective? Yeah, no, it's not. Oh, sorry, injective. We said no and I put a tick. That's silly. And surjective, no, not either, because you only get 0 in the image. And so, well, certainly not bijective then. Now the constant map. So we fix a vector u, some choice of non-zero vector u, and we map every vector in the vector space to this vector u. Sound linear? Doesn't sound linear. Does it preserve any of the operations? Does it preserve scalar multiplication? No. And neither addition. Okay, so that's clear, right? Yep, good. And then we just don't have to answer these questions. Well, we could talk about it being an injective or surjective function, but we're not so interested in that. We're just interested in linear transformations. This next one here, does that look like a linear transformation? Yeah, it sure does. And just to emphasize, we could even write it in a very sort of classical, or, you know, in our favourite kind of way, as a matrix. So it's really just matrix times x, y, z. Is it, sorry, yes, ticks those two things. Is it injective? Yeah, probably not. I mean, it's got a kernel, right? It maps certain things to other, it maps 0 to 0, but it also maps y, comma, sorry, 3y, y to 0. So no, it's not injective, e.g. That's because the kernel is not equal to just 0. So there's certainly other things that are mapped to 0 is the point. Yeah. Surjective? No, and that's because the y coordinate's always 0, so you're not getting everything in the thing. So certainly not bijective. Now let's look at these two. These next two are kind of interesting ones, in fact. So now we've got our standard, you know, like these are linear transformations written in the sort of key example way, like the standard sort of way. Linear transformation just given by multiplying by a matrix. They're certainly, okay, as I've just said, they're certainly linear transformations. We've discussed that in class. But the question is about injective or surjective. So in this one, the dimension of the image, of the codomain is bigger than the dimension of the domain. Yeah. Not surjective, good. Because if this guy was surjective, then it would say, remember we said that a basis of the, when you should map a basis to a spanning set then, but we can't do that. So because we have a basis of our n-dimensional space, we'll get mapped to n vectors over here, and that can't span an m-dimensional, a bigger, higher dimensional space. So that's a quick way of seeing that. So, because remember, there's that property. If it's surjective, then it'll map a basis to a basis over on the other side, a spanning set over the other side, sorry, spanning set. Okay, so good, no for surjective. For injective, that depends on the matrix. It certainly could be injective, but maybe not. But certainly not bijective, that's right. This one, it just depends. Just depends on the matrix. You know, if this matrix has more rows than columns, so let me just go down. So for example, if this matrix looked like 1 ... looked like the identity, and then just had zeros. What do I want? I want to make something that looks injective. So it's got more rows than columns, yeah. Yeah, I think I just continue down like that, and then zeros everywhere else. More rows than columns, sorry. That's... so that means it would stop, there'd be some 0 rows at the bottom. Now I'm confusing myself. So it's m by n, and then I'd multiply it onto n things. Oh, yeah. Okay, that's okay. Sorry. So if you took this matrix, for example, where it's got 1s as far as it can go, and then everything else just has to be 0s, then this is injective because, you know, you put a length n vector here, x1 ... up to xn equals 0. I'm trying to compute the kernel, then, I mean, x1 has to be 0 up all the way down to xn is 0. So the kernel is just 0. So that would be injective, and you could certainly dream up non-injective ones too. Just put the 0 matrix, make it completely 0, then it's not injective. Okay. So that's why it depends. For the next one, I guess we get some kind of dual situation, one would think. So now we've got more columns than rows. Yes, so now the question is, can it be injective? And the answer would be no. For a similar sort of reason, we can think in terms of that properties of linear transformations, because if it was injective, then it would map a linearly independent set in here to a linearly independent set in here. So take a basis in here, and it would map it to a linearly independent set with n vectors. But that would be a problem because n is bigger than the dimension over there. Okay, so... and this depends, and this is no. So let me just say A and B here, just to write some comments below. So for A, if it was surjective, maps a basis of Fn to linearly, to spanning set, sorry, of Fm, and that was our contradiction. In B, if it was injective, then it maps a basis in Fn to a linearly independent set in Fm, and that was our contradiction by dimension arguments. All right. Maybe I'll freeze that argument. Okay, so let's go down to a few other ones. Let's look maybe at let's look at these ones here, just for a few examples. Is this one a linear transformation? Yeah, certainly is. Maybe you just want to run through in your head quickly how that would go. You just, you know, it clearly preserves addition, clearly preserves scalar multiplication, just like very quickly in your head. So in fact, all of these three anyway, are linear transformations. The first one, is it injective? Yeah, sure looks injective. The only way you can map something to 0 would be sending A, B, C and D all to 0, and that would have been the 0 matrix to start with. Is it surjective? Yeah, sure looks surjective too, because to get any matrix, you can certainly pick an A, B, C, D that gets anything A, D, B, C on the right-hand side. So it's bijective. The next one here, similarly, they're all different, right? A, B, C, D, yeah. So these are going to be fine as well. This next one, though, of course, that's not going to be, certainly not surjective, obviously, because everything in the image insists on having the same coordinates here and here. So that's no good. But it's also not going to be injective, because take A and B to be 0, that's the 0 over here, and then C and D could be anything, and you're still mapping that to 0. Okay. So no, no, no. This last one's, yeah, what about this last one? Is that preserve scalar multiplication, addition, vector addition? Yeah, no, again, the square, I said at one time the square was suspicious and then it wasn't because it forced everything to be 0 in that case. We were working over the reals. But here, unless we say something special about this field, the square is certainly very suspicious here. I mean, if you take a linear combination, so you've got an A and an A prime, then you'd have A plus A prime all squared, and that's going to have to equal A squared plus A prime squared, and that's generally not the case. It does happen to be the case if the field had characteristic 2, so if it was F2 or F4 or F8 or F16, because then 2 is 0. So imagine expanding out A plus B all squared, you get A squared plus 2AB plus B squared, but that 2AB is dead now. So in F2, field with 2 elements, or 4 elements, or 8 elements, A plus B all squared is just A squared plus B squared. But anyway, so there might be an exception to this case if the field happened to be one of these fields. But so in general, though, let's not sort of carry on with that too much. In general, no. And there's more details in the solutions for these small fields. Okay. Good. Look, there's lots of questions. I think they're good ones for you just to go over. Let's instead move to one of these guys, if that's okay, unless there's any questions. Just to check, we can do this one. So here we've got a matrix. We're considering the standard linear transformation here. It should be M to N here. Right? M to N, yeah. This should be N to M, that's a typo. Given by just matrix multiplication, find a basis of the kernel and of the image. And anyway, this is something getting towards the rank nullity theorem, hence compute this thing, but that's the main thing is these bases. So let's do an example. Remember, we discussed how to do that. The strategy is that you row reduce this guy down, and then the columns that have the leading ones, the corresponding columns of the first matrix form a basis of the image, and for the kernel you just have to compute it by also the same row reduction. Okay, so the technique, let's do this one, but I'll give myself space here to do it. So we just row reduce 3, 6. Oh, that's in F7. I can't work in F7. That's too hard. Let's do the F5 example. My mod 7 arithmetic would just be embarrassing. So let's do this one instead. 1, 2, 1, 3, 1, 3, 0, 0. Oh, sorry, I missed a row. 3, 1, 3, 0, 0, 0. So I'm not going to have to do a great deal for row reduction here, which is good. 1, 2, 1. Now I'll add twice row 1 here. Adding twice row 1 to row 2 gives me that, and that. And well, that again. That's good. And, well, I can't help. I'll subtract the previous row 2 from the row, but or do the same thing I just did. So that was good. That row reduced very, very quickly. I've got my row echelon form here. You know, the sort of step pattern, but it just does one thing. The column with the leading one, there's only one of them here. And so I take the corresponding column over in the original matrix. This forms a basis for the image. Image. Basis of kernel. I have to actually just compute. So to compute that, I just remember if I was computing the kernel, I'd be solving the matrix equation with 0, 0, 0, 0 here, doing the row reduction. I don't have to actually put the zeros because obviously whatever row operations I do, they stay as 0, 0, 0, zeros. So I just have to solve. Just imagine the zeros are there now. Maybe I'll put them on in another colour. 0, 0, 0, 0, just so we've got them there. So we'd have two free variables. Let's call them y and z. So y equals t or something is free, z equals s are free. In the field is F5. And then we can solve for x in terms of those free variables. X is then minus 2y, which was t, minus z, which was s, which perhaps I'll write in F5. It's a bit better to write that as 3t plus 4s. So that says my kernel is equal to the set of all things of the form 3t plus 4s t s, such that s and t are in the field. But that equals the span of this guy, 3, 1, 0, that's the t, multiples of t of that guy, and s is this guy. And when you do the calculation this way, I've said a few times, the way when you think about it, think about how it works, you automatically get a basis there. And it's always because there's there'll be zeros in different places. So clearly any linear combination of these two which equals 0, this one forces that coefficient to be 0, and this one would force the coefficient of that vector to be 0. Okay? So that's our basis for the kernel. And so the rest are all the same, so just harder calculations in F7 or whatever. So reduce this down to row echelon form. Identify the columns that have the leading entries, leading ones. The corresponding columns over here form a basis for the image. And the same working then by just doing the free variable calculation like that gives you a basis for the kernel. Okay, so do all of those. Make sure you know how to do that in your sleep. Oh, sorry, and this last one, say again? Yeah, that's right. So this one here, it's the dimension of the image, the domain, the Fn. So the dimension of the kernel here is, where are we? Down here is 2. The dimension of the image is 1. And the observation is 2 plus 1 equals 3, which was the dimension of the domain there. And that's the rank nullity theorem that we'll discuss again next week. Okay, excellent. See you indeed next week.
Hey again.
I'll do that.